Welcome. This is the topic on strength of materials, thin cylinders and spheres. And today we will be seeing about introduction of thin cylinders, expression for stresses in thin cylindrical vessels subjected to internal fluid pressure, related numerical problems. We will be seeing the applications of these thin cylinders. So let us get into the topic. So here this is the introduction. So let me read the point here. If the thickness of the cylinder is less than 20 times the internal diameter of the cylinder, then it is considered as a thin cylinder. Otherwise, it is a thick cylinder. That means the thickness of the metal. So, for example, this is the cylinder. It is a thickness. That thickness should be less than 20 times the 20th of the diameter. It should be less than. Then only we can say this is a thin cylinder. Otherwise, it will be a thick cylinder. So it has many civil engineering applications, many mechanical engineering applications and industrial uses, and mainly we use thin cylinders for storing liquids, gas or fluids, for transporting and storing. So for example, pipes, you may see boilers, storage tanks, all these come under thin cylinders which are subjected to internal fluid pressure, and these cylinders are subjected to internal fluid pressure. So we can see some examples over here. There's a storage tank, these are pipes, this is another storage tank, this is also another storage tank. So some of the storage tanks can be placed, can also be transported. So inside the gas may be there, inside the fuel may be there, petrol, diesel, like this, and gases may be there. All will be stored in a thin cylinder. You can easily understand these are all subjected to the pressure from the fluid which is there inside, right? So let us see technically what are the stresses in thin cylindrical shell. Um, so first one is circumferential stress, hoop stress. That means, so here along the circumference the pressure will be acting like this, right? That is circumferential stress. So due to circumferential stress the failure may occur like this. So it will be burst into two parts. And second one here is longitudinal stress. Here it is longitudinal stress that acts along the length. So internal fluid pressure, it will be acting in all sides, longitudinally and circumferentially, but we are dividing them. With circumferential, stress will be there due to internal fluid pressure. With the same internal fluid pressure, the longitudinal stresses will also be developed. So what will happen if the stresses are acting like this? So it will be cut into two parts, isn't it? So that is longitudinal stress and radial stress. So all these stresses are internal resistance due to that fluid pressure. Stress is the internal resistance offered by the body against external force. So that is nothing but here the internal fluid pressure, and that will be resisted by the stress in the material itself. Next one is radial stress. That is actually compressive in nature. It is actually compressive in nature, and this is acting on radial direction. Radially it will be acting, and it is from the outside. For example, if you burst the balloon, what will happen? It will burst off, right? And if you burst that car tire, what will happen? All the tire will be, the external parts will be compressed. It will be compressed, right? That is nothing but it is having a lot of radial stress. But in thin cylinders the thickness itself is very less, so we cannot expect radial stress will be existing. If it is so existing, that will be having very less value, that can be negligible. So we can neglect that. So we have to see now circumferential stress and longitudinal stress. We shall see them one by one. First let us see circumferential stress or hoop stress, right? Circumferential, I have told you how the failure occurs. So due to circumferential stress, so due to internal fluid pressure, that will be divided into two parts like this. So here it is internal fluid pressure, you can see small p is acting over here, and here this is sigma h hoop stress, or you can say circumferential stress. I say sigma c here, right? So what will happen, why it will burst? Because every material will have some resistance. That internal resistance offered by the body should resist the tensile force offered by the fluid inside. Then the pipe or then the shell will be safe. Otherwise, if the internal fluid pressure is dominating the resistance offered by this pipe, then it will fail. So that is simply, I can say, bursting force should be equal to resisting force for the limiting case. For equilibrium condition, I say, or for the limiting case, I say bursting force is equal to resisting force. Let us see what is bursting force. Bursting force, that is nothing but internal fluid force due to internal fluid pressure. Force due to internal fluid pressure. That is nothing but small p, that is the internal fluid pressure. I am calling internal fluid pressure as small p multiplied by area on which p is acting. So I will say small p multiplied by, so where it is being failed, in this portion, right? In this portion it is being failed. Excuse me. So in this portion, right? This portion, at this portion, the material is being cut into two portions. So can you tell me what is the area of that? That is internal diameter small d multiplied by the length. That is nothing but d into L. That is the area, right? PdL. Take it as equation number 1. So we have seen bursting force. Let us see now resisting force. Resisting force. That is internal resistance offered by the tube. So that is also called as circumferential stress. Here you can see the arrow marks. Those arrow marks are showing how the internal resistance will happen. So in this way, so it is resisting the fluid pressure. It is trying to keep the tube as it is. So sigma c is acting over there, that is the stress. How will you calculate the force now? So I am telling as stress is equal to force by area mathematically, then force is equal to stress into area. So in order to calculate the resisting force, what I have to do? That resisting force is nothing but the sigma circumferential stress is nothing but sigma c multiplied by area on which it acts. Force is stress into area it acts. So sigma c, and where it is acting? So in the diagram you can see this is shaded portion. At this shaded portion it is acting, that is having a thickness small t into along the length. I will show you here. So at this portion it is acting, right? So that is nothing but thickness small t here, small t multiplied by the length, this rectangular portion. And two types of rectangles are there here, two edges are there. So this is also t into L two times, t into L two times, because two rectangles are there. So now how will you calculate? Sigma c into 2TL. For the limiting case, I said bursting force is equal to the resisting force. So equate equations 1 and 2. What will happen? P into dl is equal to sigma c into 2TL. So that is nothing but sigma C can be written as PdL by 2TL. LL cancel, PD by 2T. Take it as equation number 1. Right? So that is about circumferential stress. Let us move to longitudinal stress. Yes, longitudinal stress. Initially we have sigma C is equal to PD by 2T, and we have taken that as equation number 1. And now let us see longitudinal stress. This is how it is acting. So here it is acting in the length direction. P is acting. So P always acts in all sides, but we have divided it into two types. One is circumferential, another one is longitudinal, but they can act both together. Right? Then what will happen? It will break here. Say section AB. It is breaking at section AB, and here this is thickness small t. Right. So here also we have to see when will the failure occurs. When will the bursting happens? If the longitudinal stress developed by the if the longitudinal force developed by the internal fluid pressure dominates the internal resistance offered by the metal, then the failure occurs. Right? So let us see now. Bursting force is equal to again resisting force. Resisting force. Bursting force, let us see. Bursting force is nothing but internal fluid pressure, force due to internal fluid pressure. Right? That is nothing but small p into area on which it acts. So that is nothing but p into, so where it is being bursted here in the shaded portion. So that is exactly where p is acting and causing the cylinder to burst. And the area is nothing but simply area of the circle, pi by 4 d square. Take it as equation number 3. And resisting force, and what is the resisting force here? Longitudinal stress. That is longitudinal stress, and I am indicating with sigma L multiplied by area on which it acts. So sigma L into area, here in this portion it is acting. In this portion it is acting along the thickness. Thickness it is acting, sigma L multiplied by the area. What is the area now? Can you guess? Here this is nothing but circumference of the circle, that is pi d or 2 pi r. I am taking pi d here multiplied by thickness. So that will give you area of the ring where sigma L is acting, and take it as equation number 4. And for the limiting case, I said bursting force is equal to resisting force. Let us equation number 3 and 4. What will happen? P is into pi by 4 d square is equal to sigma L into pi d into t. So sigma L is equal to P into pi by 4 d square by pi dt. D square cancelled, pi cancelled, that is remaining is PD by 4t. Take it as equation number 2. So initially what we have equation, first equation, sigma C is equal to, yes, sigma C is equal to, we have PD by 2t. So from this I can write sigma L is equal to half of the sigma C, or simply you can say sigma C is twice sigma L. that is circumferential stress is twice the longitudinal stress, or longitudinal stress is half of the circumferential stress or hoop stress, right? And here we will take for the principal stresses we consider sigma c as sigma 1 and sigma L as sigma 2. Both are tensile and both are mutually perpendicular. So one is acting in this direction and then another one is acting in circumferential direction. So both are perpendicular to each other, and if you consider the maximum value will be sigma c. If you compare these two values, by the equation itself you can say sigma c value will be more than sigma L value. So sigma c will be considered as maximum primary principal axis, and this is minor principal axis. With that, you can find out maximum shear stress as sigma max is, by default we have sigma 1 minus sigma 2 by 2, that is nothing but sigma c minus sigma L by 2. So sigma c is here PD by 2t and this is PD by 4t by 2. So by solving you will get sigma PD by 8t, and here this is PD by 8t, that is the maximum shear stress, tau max. So this was given in the notes given in description below. You can download it and please verify. So let us move to numerical. Here this is the question I have given to you. So let us solve this now. So a water main 80 centimeter internal diameter contain water at a pressure, how much? Pressure head. It is not given pressure directly, it is just pressure head. How much? 100 meter. If the weight density of the water is 9810 Newton per meter cube, find the thickness of the metal required for the water main. Given permissible stress is 20 Newton per mm square. Here water main has internal diameter small d is given. So let us write the given data first. Small d is 80 centimeter, that is nothing but 800 mm. Pressure head is given small h, 100 meter. The weight density of water is given. What is the weight density of water? Small w is 9810 Newton per mm square, and they are asking us to find out thickness. And the permissible stress is given as 20 Newton per mm square. So always permissible, when the permissible stress is given, that should be taken as sigma c, not sigma L, because sigma c value will be greater. So we have to consider it as maximum one. So always sigma c is less than sigma L. If you design for sigma L, that will not be compatible or acceptable for this to bear circumferential stress. So let us find out. Sigma c is actually PD by 2t, as we have seen in the previous derivation. Small p is not given, we need to find it out. The pressure can be found out from the fluid mechanics. WH, it is said as the weight density of water multiplied by the pressure head, that is 9810 Newton per meter cube, sorry, Newton per meter cube, and here H is 100 meter, right? So that is how much? 981000 Newton per meter square. I want to convert into Newton per mm square. What should I do? 981000 by 10 cube, because 1 meter is 1000 mm whole square. Now I can write Newton per mm square. Now P is, I say, 981000 by 10 power 6 Newton per mm square, right? And we can now find out the value of T, because all the parameters are known. Sigma c is equal to PD by 2t. Here we have the value of sigma c as 20 and small p we just got it as 981,000 by 10 power 6 multiplied by diameter is how much? 800 mm by 2 into thickness. We need to find out the thickness. So only unknown value is here, small t. So by solving it, you can get the value as 39.2 mm. Thickness is 39.2 mm. So you can these are all simple applications based on the covered derivation topic. Here I have a homework problem for you people. You just do it and mail me. I will show you the question now. Here it is, your homework. So please solve the problem and take a photograph and send it to my mail ID. Here this is my mail ID. Please do the question and send it to my mail, and the link and clue for this question is given in the notes, which is the link which link is mentioned below the description. Please go to description, see the link, go to the link and download the notes and see the topic and do the question. Please send it to my mail ID. Thanks for watching.